Okay, at the end of previous week's lecture, we had looked at this flowchart, and this sort of describes the flow of a complete finite element code. We had gone through all the steps for the truss except for this particular step, which involves the solution of the modified stiffness matrix, modified after applying the boundary conditions, and the modified force vector. So this is no longer singular, so you can take its inverse, multiply it with f prime, and get the solutions to the degrees of freedom, displacements in our case. So when you do this solution, you will get the displacements of the fixed nodes to be exactly what they are supposed to be, and for the other nodes you would get a proper solution. Now this solution procedure is in many ways the heart of a finite element code, and it takes up most of the time in this whole procedure. So this solution procedure has to be understood in some detail, so I will spend this week making you aware of the solution procedures that are available. We will not be able to go into all aspects of the solver technology, and this is an evolving field and there are many powerful solvers available. But in general, there are two kinds of solvers that solve equations of this sort. They are called the direct solvers and iterative solvers. So traditionally in finite element method, direct solvers were preferred because direct solvers give you a solution to you in a specified number of steps after a specified number of operations, and you don't start with any guess, whereas in an iterative solution you start with the guess solution, and then the iterative solver works through in a priori unspecified number of steps to try and converge to the actual solution starting from your guess solution. So traditionally all solvers used to be direct solvers, but as computers are getting more and more powerful and parallel computation, especially in finite elements, is taking root, iterative solvers have become fashionable, useful at the same time. And towards the end of this lecture, we will touch upon some of the major iterative solvers that are used today. However, most of the time will be spent on looking at direct solvers, and there are various varieties of direct solvers. We will not be able to look at everything, but the most of the direct solvers are based on a process called Gauss elimination. So the Gauss elimination process for solving a matrix equation of this type has been around for many years and forms the basis of many direct solver techniques. So we will illustrate this with an equation of this form, where X is what we want to solve, A is an n cross n matrix, B is an n cross 1 vector, and X is, after it's solved, is going to be an n cross 1 vector as well. A is, in all the cases that we are going to look at, A is going to be square matrix, which is also invertible. In our case, we actually want to solve k prime u equal to f prime, where k prime is positive definite. That means all its eigenvalues are positive. K prime is also symmetric as well as banded. Banded meaning that most of the region, many parts of k prime are actually zeros, and k prime is symmetric as well. These we have discussed, and we will discuss further on these points. These are actually mandated by the nature of the equations in solid mechanics. So the nature of the equations actually make k prime symmetric and make K prime banded. Bandedness also depends on the node numbering. So the node numbering decides the bandedness. Better the node numbering, thinner is the band around the diagonal, and the symmetry is decided by the nature of the problem. Positive definiteness is also um, dictated by the nature of the problem. But at this moment, we will assume that when we solve an equation of this sort, A is a symmetric and positive definite matrix. Okay, so let me first explain the Gauss elimination process, and let me explain that through a small example. Let us demonstrate the basics of Gauss elimination process through this small example. So this is the original problem, and to do Gauss elimination, what we start by doing is multiply the first row by, let's say, this quantity in the second row just below 1 1. So we multiply it by minus 6 by 18, and then subtract the multiplied first row from here, from the second. So this will become 0, and these will become some other numbers. So this will be also get multiplied by minus 6 by 18. Then you subtract it from 12 and you will get 10. This will also get multiplied by minus 6 by 18. Subtract it from 0, you will get minus 2, and so on. So the main point is that this is going to become 0. Then we go to the third row and then multiply this by again 6 by 18. The third row, 3 1 is also minus 6. Divide by 1 1 to get minus 6 by 18. Again subtract it from here. This will become 0. These will become something else. So this has become 0, and these will become something, whatever comes out by multiplying this by minus 6 by 18 and subtracting from here. Similarly, the fourth row is already 0, so we don't have to do anything. We actually multiply by 0 by 18 and then subtract. It remains as it is. So this is what we have. So now, after this is called the first elimination step. This is called the first elimination step. Then after the first elimination step, everything under 1 1 has become 0. Now we start with the second elimination step, and the second elimination step starts from the result of the first elimination step. So again, what we do is we now want to make these two 0. So what we do is first we multiply this by minus 2 by 10, and then multiply the whole row by minus 2 by 10, and then subtract it from here. So this becomes 0 like it has here. These become something else, whatever you get by multiplying minus 2 into minus 2 by 10 and subtracting from here. And in the next step, we want to make this 0. So what we do is multiply it by minus 6 by 10 and subtract from here. This becomes 0. So these two have become 0, and these have changed to whatever they have changed. Okay, so now we will do the final step. We will take this and try to make this 0. So here we will again multiply by minus 7.2 divided by 9.6, subtract it from there. This becomes 0 and this becomes something else. So at the end of 1 2 3 steps, in the fourth step, what we have is a matrix where everything under 1 1 2 2 3 3 etc. are 0. So the matrix is called upper triangular. So this is an upper triangular matrix. Now why is this a good idea? It's a good idea because in the from the upper triangular matrix, now we can start the process of back substitution, meaning that we can immediately find U4 as 45 by 3. So once we have found U4, then we go to U3. U3 is 9.6 U3 minus this equation, sorry, this third equation is 9.6 u3 minus 7.2 u4 equal to 44. That's the second equation from the bottom, but we already know u4 from the first step. We know u4 is equal to 45 by 3. So we just plug in there, take it to the other side, and we get u3. So this is called the process of back substitution. So we get u4 right away. Then u3, once we know u4, we get u3, then u2, u1, and we go in the reverse order and get all the variables exactly at the end of these back substitution stage. So that's the, in a nutshell, how Gauss elimination applies to a matrix equation. Now, one problem that you might have envisaged is what happens if during this process one of these diagonal elements becomes 0, because you are dividing by the diagonal element at an elimination step. So if one of these diagonal elements becomes 0, then you have a problem, and this basic Gauss elimination process will actually stop. In that situation, if this happens, in that situation we resort to something called pivoting, which we'll have to understand a little bit, and that I'll do in the next lecture.